Section 5.4, day 2, right? Whoa. All right, so one of the things that we had done last time is we talked about basic antiderivative rules. So before we get too far into this, let me just remind you those basic antiderivative rules. That's what's on this page. We have the constant rule that says that if you have a constant and you take its antiderivative, you just reattach x. So it becomes kx, and then we put plus c on the end of everything that we do, right? So when you do your quiz on Tuesday next week, my suggestion is way at the top of your page, you write down plus c really big so that you don't forget plus c's on any of your problems, okay? The second one was a simple power rule. So for the simple power rule, you increase the exponent by 1, and you divide by the new exponent. And then you put a plus c on the end. The natural log rule is something we didn't have when we did derivatives. But we had the reverse of it where we had the log rule, okay, the natural log rule. But we started as a natural log and it became a 1 over x, and so now we're going backwards. The antiderivative of 1 over x is natural log of x. But we have the caveat that we can't have inputs into logs that are negative, so we have to put the natural log of the absolute value of x to make that work. The exponential rule, that's the b to the x rule, its antiderivative is b to the x divided by natural log b, whereas the derivative rule was b to the x times natural log b. E to the x rule, e to the x, its antiderivative is e to the x. Super friendly, the best one ever. And e to the ax would be e to the ax divided by a as opposed to being multiplied by a if you were doing the derivative. Constant multiplier says that if you have a multiplication factor, that's a number times the function, the number just comes along for the ride. So we keep the number and we take the antiderivative of the variable component. And then a sum difference rule says if we have two components that are added or subtracted, we just take their antiderivatives separately and we add or subtract them back together at the end, which is what we did for derivatives as well. So this is where we were last time. We had done 3 examples, and we are on this one now. This one has context. So it says, find the general antiderivative for the function c of x equals 0.8 over x plus 0.38 times 0.01 to the x dollars per unit squared when x units are produced, and then label the units on the antiderivative. Normally they don't tell you the labeling part, they're just going to assume you did it. They're probably going to say something like find the general antiderivative model. That's kind of one of those keywords that they like to use when they want the language. This one actually wrote it all out for us. Okay, so as with the case last time, when we take antiderivatives, we change them from the lowercase letter that we're given to a capital letter. All right? This one's kind of not happy and not friendly because we're using c, and we're going to put a plus c at the end of this thing too. So please understand that this c of x is the name of the function and the c at the end is just a constant. Maybe we'll put a plus k at the end just so that we don't actually make that look weird. But they're not the same variable, okay? So capital C of x. This is 0.8 divided by x. Okay, the 0.8 is a constant multiplier, so it's just going to come along for the ride. What happens when we take the antiderivative of something, usually 1, over x? We get a natural log. So on this one, we've got 0.8, because it's a constant multiplier, and then we have the natural log of x. So the 0.8 is coming from here. The natural log x is coming from the x in the denominator. Now notice that's only x in the denominator. If there were a number in the denominator or x to the 2 in the denominator, that's not the natural log rule. Okay, it would look different. So just because there's a variable in the denominator does not actually mean that you automatically go to logs. But if it's x to the power 1, then you will. All right, the next component has 0.38. Again, it's a constant multiplier, so it comes along for the ride. What do we do with 0.01 to the x? Good. It's the it's the exponential rule. So Kendra's kind of quiet, but she's exactly right. It's 0.01 to the x. And I had actually we had a conversation about it. That x can be on the inside of the parentheses or the outside. It doesn't make any difference because 0.01 is going to still be raised to the x either way. And then we're going to divide by, you can divide it right here, or if you want to divide the whole thing, it doesn't matter, by the natural log of 0.01. Okay, so when we're finding antiderivatives, we're always going to put a plus c on the end. Because our function's name was c, I'm just going to put it as a plus k. You know, we can pretend like k stands for constant. It's got the same sound, right? Sure. Yeah, cool.
Do we need the absolute?
On this piece, we do. Yes, I left it off. Thank you for catching that. On this one, if you didn't have it, you'd probably be okay. Does anybody know why you could be okay on this one? X can't be negative. Why? Not because it's on the bottom. What is X? Nope, X is not dollars, but you're getting closer. It's what? Do you see that? X is units produced, and can you produce a negative number of units of anything ever? No, you can't produce a negative number of units. So if you left it off, you'd be okay because of the context that forces this value to be positive anyway. If you put it on, you're more than okay because then you've covered yourself either way. Does that make sense? Okay. Thank you for checking that, Cole. I appreciate it. All right, so this is our function in terms of the numerical values and everything, so we're good on that part of it. Now we need the units. So let's take a look at the units that we were given on this problem. It starts out with dollars per unit squared. And then your X is in units that are produced. So what happens when you multiply dollars per unit squared times units? Because that's what area does, right? One of the, careful, what cancels? One of the units. So let me write down sort of the visual of what's going on. You've got dollars. I know. And here's units squared. And you're multiplying by units. So this units is going to cancel out with one of the squared units on the bottom. So what are you going to be left with? Dollars per unit is what's going to be remaining. So this is dollars per unit. And then the nice thing about when you're doing either derivatives or antiderivatives is you just rewrite how the X is determined because it never changes. So since here X is units produced, you're going to say the same thing here, where X units are produced, or where X is the units produced, or something like that. Yes, ma'am.
Why are you multiplying by units?
Remember when we created our section 5.2, the one that you just turned in, we talked about the fact that antiderivatives are measuring area under curves. And when you measure area, you're measuring length times width. Basically, you're making a whole bunch of very small rectangles. So the width is the X units, and the height is the Y units. So it's the units you're multiplying by each other. That's why. Okay? Any other questions about this part of this? Okay, we have another example. The language changed. What about the language of this problem is different than the last one? Yeah, there's a word here that we have not done anything with. It's the word specific. What was the word we had on the last problem? General. Okay, so let's talk about what general versus specific means in these problems. The word general means that your equation has a constant that's added at the end, plus k plus c, whatever, okay? That's what general means, that you've got that variable that you don't know what that number, it's not even a variable, it's a constant, you just don't know what it is at the end. So the fact that this says specific means that when we're done with this problem, completely and totally done, there won't be a plus c at the end. And the reason there won't is because we're going to figure out what the value should be at the end instead of just leaving it as plus c. Now, if you'll notice, the way that we're going to do that is we're actually given more information on this problem than we were on the previous problems. This piece right here has a name. It's called an initial condition. And it means that as we work this problem toward the end of it, we'll be able to use that to figure out what C is. Okay? So, we're going to start the same way we did before. We're going to take our equation that we are given, which is this piece, and we're going to find the general antiderivative. So this is a lowercase f of x, so we're going to find a capital F of x. And we're going to go through it just like we did in the last problem. So this is 3.2 x to the 0.23. Well, the 3.2 is going to stay. What am I going to do to the x to the 0.23? Add 1. So this will be x to the 1.23. And then what? Divide by the 1.23. You can write that like it's the x that's divided by or by the whole quantity. It doesn't make any difference. All right, how about this plus 4 at the end? Yes, Lainey.
There's no f of prime, like f,
That's because they did a lowercase f here. So we changed it to a capital F.
but it's not f of, like it's not the derivative.
Where it is the derivative, the notation is that we're finding the antiderivative of what we were given.
Wouldn't it be f of prime with x?
F prime is a derivative. We're not finding a derivative, we're finding an antiderivative. It's like over here when we did these. Do you notice this went from y to capital Y? That's the same thing we're doing. The notation that's mathematically accepted is that we capitalize the value when we're finding the antiderivative. Now, if we had started with a prime value given, like this one, no, this one wasn't either. It was a lowercase. See how this is a lowercase and we turned it into a capital? We did the same thing here. Occasionally, they will start with where they give you the f prime of x and they're asking you to find the antiderivative and you find f of x. That's okay. So it could look like that, but if they start out with a lowercase like this,
Just capitalize it.
the notation is to capitalize it. Yeah. Yeah. Okay. Whoops. There we go. 4. We're on the 4. What's the antiderivative of 4? 4x. And then we need a plus c. You have so far found the general antiderivative for this problem, the general antiderivative. But you have this piece of information over here that you can now use to find the specific antiderivative. Now, if you remember from this notation, what it's telling you is that you have the x value of 2. So everywhere you have an x, you're going to plug in a 2. And it's telling you the output value, that is what's on the left-hand side, is 7.8. So in our problem down here, we're going to be able to replace this side is 7.8. The 3.2 stays. Your x value is, what was it, 2 to the 1.23. Is that readable enough in that green? I think it's okay. Is it okay? Yeah? Dakota?
So we add 1, but it says 0.23 and then.
Uh-huh.
Oh, so you-
Right, because it's the power rule. The simple power rule is that you increase the exponent by 1. Yes. And then we're going to divide by the 1.23. We've got 4 times the 2 plus c. So notice the only thing you don't know in this equation is the c, right? So let's simplify what we have. The left-hand side you have 7.8. I need you to take your calculator and to figure out what is 3.2 times 2 to the 1.23 divided by 1.23 plus 8. We're just going to enter everything that's on the right-hand side of the equation except for the plus c, because we don't know that quantity, right? And find out what value it gives us on the left-hand or on the right-hand side before the plus c. So I see many calculators out. That's a good thing. What'd you guys get? What'd you get, Luke?
14.102. Well, 103.
Okay, so 103?
Yeah.
Okay. All right, 14.103. Is that what you guys have? Excellent. So now what am I going to do to figure out what C is? Subtract. So this is basic algebra at this point. I need 7.8 minus 14.103. What is C? Negative 6.303? Do you guys agree?
Yes.
Excellent. It's really tempting to think you're done with the problem because you have found C, and that is what you were looking for. But you didn't really answer the question they asked yet. They asked, what is the specific antiderivative? So that means that we need to take that general antiderivative we found up here, and we need to write it out with the C in the location where the C was holding the place earlier. So f of x equals 3.2 times x to the 1.023 divided by, I'm sorry, that's not 0.23, 1.23. There we go. Divided by 1.23 plus 4x minus 6.303. That's the specific antiderivative. Hannah.
Okay, so when you do, when you're finding the antiderivative
Uh-huh.
of the x to the 1.23, with the 3.2 along with it, do you divide the 3.2 and the x to the 1.23?
It doesn't matter because essentially you've got things that are all multiplied together. I know that this sort of looks like you've got division. I get that. But all of those quantities are really multiplication, and multiplication is commutative, so it doesn't matter what order you do it in. So you can think about this as 3.2 times the x and then all of it divided by the 1.23. You can think about the 1.23 only dividing the first part and then being multiplied. It won't make any difference on how you write it or how you think about it because you'll get the same quantity if you plug anything into it. Yep. Okay, one more problem, and I think it's one we've seen before. Have we seen this problem before? A lab mouse problem. I think you've seen it twice, actually. I think you've seen it in class, and you've seen it on a homework problem asking slightly different questions. So let's revisit it. The rate of change of the weight of a laboratory mouse can be modeled by the equation W of t equals 7.37 over t grams per week, where t is the age of the mouse in weeks beyond 2 weeks. At the age of 9 weeks, a mouse weighed 26 grams. Find the specific antiderivative, there's that word, specific antiderivative, describing the weight of the mouse. So we're starting with a lowercase w of t equals 7.37 divided by t, and then it says grams per week. So we'll deal with the units later. What we're first going to find, though, is the general antiderivative. So lowercase w becomes a capital W. What is going to be the general antiderivative of 7.37 over t? Okay, this is another one where if you did have accidentally or on purpose leave the absolute values off, it would actually be okay because this is the age of the mouse beyond 2 weeks business, which is the only thing that makes sense for the context of the problem. That's a positive amount of weeks beyond 2 weeks, so it'd be okay. For safety's sake, I would encourage you to leave them on there just so you don't have to try and think about, do I need it, do I not need it? If you always put it, then you're on, you're erring on the safe side on that. And then I need one more thing on this, plus c. All right, so I'm supposed to now find the specific antiderivative. That is, I'm supposed to figure out what is c. How am I going to do that? What other information is going to be useful to me in this particular problem?
The mouse weighs 26 grams.
Yeah, good. The age of the 9 weeks, the mouse weighs 26 grams. Okay, so where's the 26 gonna go?
Left side.
On the left side, because that's the weight. And what is going to go for t?
9.
Be careful.
7.
7. Why is it 7 and not 9?
After 2 weeks.
Yeah, because it's supposed to be how many weeks old it is beyond 2 weeks. So it's 7 weeks beyond 2 weeks to make 9-week-old mouse. All right, so you're going to do the same thing you did on the last problem. Find out what is 7.37 natural log 7. And let's get a 3-digit decimal expansion for that.
14.341.
Okay, and then we're going to subtract the 14.341 from both sides. So what will C equal?
11.659.
Does everybody get 11.659? Yeah? Okay, good. So am I done? No, I'm not done. What am I going to have to do to actually finish this problem? Rewrite it, and I need to do units. I have 2 things to do, actually. Okay, so capital W of t equals what?
7.37, natural law, plus 11.61.
Okay, so that's all of the numerical component of this, right? Then I need the units part of this, so let's go back up and look at units on the original problem. The units says that this is in grams per week, and it's telling us that the T is being measured in age of the mouse in weeks. I know it says beyond 2 weeks, but that won't affect the units on the output. So if I have grams per week, and I multiply it, remember this is an area, and I'm multiplying it by weeks, what do I end up with? Grams. So this is grams, where T is what? The age of the mouse in weeks beyond 2 weeks. All right, any questions on that one? All right.